Hello, my name is Jack Massey and my project is on sinkholes. As many of you might know, sinkholes are very common in Florida. My project will be attempting to identify areas in Florida that are high risk, and within those high risk areas, where would the sinkholes cause the most damage? Florida has a very unique geology, as much of the subsurface consists of limestone. This limestone acts as an aquifer, containing the water that the state uses for drinking and other purposes. However, over time, this limestone can dissolve and create gaps in the subsurface. If the limestone is dissolved enough, the subsurface overlying it can fill the gap and create holes on the surface. This obviously is very dangerous and is known as a sinkhole. It is important to identify the high-risk areas to aid emergency services. The purpose of the study is to combine known factors of sinkhole formation to identify high-risk areas. After that, we will look at areas in the state that have higher concentrations of population with higher property values, and this would indicate where sinkholes might do the most damage. The study will revolve around rasters that correspond to sinkhole formation and rasters that correspond to high population areas and high property values. Manipulating and combining these rasters will give us a picture of where sinkholes occur the most and where they do relatively more damage to provide emergency management with the blueprint as to where to concentrate resources. The problem statement is, where are sinkholes most likely to form in Florida and where would they do the most damage? There are the key words. According to a recent study done by the Florida Department of Environmental Protection, the two most important factors that initiate sinkholes are the amount of overburdened sediment thickness on top of the top limestone layer, as well as the difference between the groundwater level and the top of the limestone surface. These two factors are important because less overburden thickness on top of the limestone allows water to penetrate into the subsurface limestone more quickly and efficiently. The difference between the groundwater level and the top of the limestone surface is important because less difference between the two shows us where water table fluctuations or hydraulic pumping would be the most prevalent, which would indicate areas where flushing of sediments within the cavities would dissolve the limestone most quickly. According to their research, areas that have less than 133 meters of overburden sediment thickness and areas with water table difference in top of the limestone surface less than 96 meters were the most indicative of sinkhole formation. After we get an idea of where the higher areas of risk are, we will attempt to identify where within these areas have the most people and the most property value. We will do this by looking at census data and highlighting census block that shows more population than the mean and a higher income median than the mean. Combining the high-risk areas with high population and median income areas will give insight into where sinkholes will cause the most damage and to where to focus resources for risk management. The study area is obviously Florida, the state of Florida, and the audience will be anyone concerned about emergency management. We have our 5 layers, our background layer, our census data, and then the 3 raster layers that correspond to sinkhole formation. Here are the actual rasters. We have depth at top of limestone, elevation of Florida, and the water level at May 2016. These are all in meters. Our other 2 rasters are income, median income for Florida census counties, and the population for each of the Florida census counties. After getting my 5 layers into ArcMap, my first step would be to make sure all my layers are in the same projection. I will use NAD 1983 Harns-Alvarez. The projections my 3 raster data layers are as a I will use the projection tool on the background layer as well as the other 3 rasters. To begin, I will start identifying areas within Florida with the greatest risk of sinkhole formation based off the 2 important predictors of sinkhole development. The first predictor we will look at is amount of overburden thickness. To produce overburden thickness, I will need to use math, in this case, the minus tool. Subtracting the limestone surface from the elevation surface, we will return the amount of thickness between these two layers. In our new layer, I will define anything less than 133 meters of overburden thickness, as defined by the Department of Environmental Protection, as a high-risk area. We will essentially do the same thing for the next predictor. We will use the minus tool, subtracting the water level surface from the limestone surface. Areas with differences less than 96 meters, as defined by the Department of Environmental Protection, will be defined as high-risk areas. To define high-risk areas in both of these new rasters, we will go into symbology and define the intervals. We will need to combine both of these new rasters into our final high-risk area map. I will use the plus tool, which will combine both differences and give us a raster that shows that. If the total differences are less than 229 meters, they will be defined as high-risk areas. Just like before, we will go into the symbology tab and define that as such. To isolate high-risk areas, I will use the raster calculator. I perform a function that isolates anywhere on our raster that is less than 229 meters of difference. Doing a select by attribute will export the layer, and we will have our final high-risk area raster. Our next objective will be to define areas in Florida with relatively high populations and property values. I will define both of these values where they are anything higher than the mean, which I can find in statistics. To do this, I will actually need to copy the census block vector layer. On the first one, I will specify the layer property by total population, and the second one, I will specify it by median income, which in this case will correlate to property value. I will need to convert both of these vector layers to raster layers because this will be useful in my math algebra. After looking at the statistics, I found that the mean population and median income in census blocks are 1,740 people and $46,000 respectively. After performing the necessary map algebra, the new layer will highlight areas of relatively low or high population and median income numbers. Again, like before, I will select by attribute to isolate the relatively high regions. Our final step will be to perform another map algebra calculation, making a final layer that combines areas of higher sinkhole risk with areas that have been defined as high population and high property value. Select by attribute will isolate my desired criteria and create the final raster. This final raster will be placed on a background layer, which will give context where in the state sinkhole poses the most danger in terms of loss of life and property damage. Here are the overview of my methods. I use the minus tool, the plus tool, select by attribute. I specified my vector layers properties. I use conversion to get them to rasters, and I use the raster calculator various times to specify the meters and the people and the money correlating to income values. Here we see my flowchart of methods. My results are fairly straightforward. My map algebra has created 4 maps that can be seen in my screenshot of results, correlating to each piece of evidence. The first 2 that were the things that indicated sinkhole formation were overburden thickness and difference between water level and limestone. Here we see those. On the left, we see overburden thickness. On the right, we see the difference between water level and limestone. They look fairly similar. We combine these 2 to make this map, the favorability of sinkhole formation. Areas in blue are defined as higher risk. This next raster was combined from the population and income rasters, and the areas in purple highlight areas where the population is over the mean and the income values are over the mean as well. And that is our final map, combining both of the previous 2 rasters, showing areas for most indicative sinkhole formation and where areas where within that would be that would have the most damage. So areas of green are going to be defined as areas of concern. The areas highlighted in green are in the final map, like what I just said. We see that most affected areas in Florida are going to be in the north central parts, specifically on the western and eastern coast of this subsection. As far as counties go, we see that Hernando, Citrus, Marion, and Alachua concern in the Big Bend. To the east, we see Volusia, Seminole, Brevard, and Brevard counties are most important. And there is also a small portion of the Panhandle that is most affected. This final map can be given to an emergency management team as where to concentrate resources to prepare for future sinkhole events, or as a guide to where to bring resources after sinkhole triggering events are observed. Here are my limitations and discussions. And finally, here is my self-evaluation. I'm pretty satisfied with the project. That the results turned out pretty well. I think one of the biggest upsides was that I was able to learn and interact on how to extracting GIS data, as well as combining everything and making a final map, which I actually found fairly difficult.